Hi, I'm Michael Gevelber, professor of mechanical engineering at Boston University. I work in building energy systems, and I'm the moderator for today's program. I'd like to give you a warm welcome to the first of our seminar series on decarbonizing existing commercial buildings, presented by Boston University's Institute of Sustainable Energy. Today's session will focus on the technical issues and opportunities, and in a month, we will hold a session focusing on policy and financial issues. With the backdrop of the ongoing COP26 meeting, why did we create this seminar? Simply put, the US needs to decarbonize as quickly as possible, and existing commercial buildings provide an important opportunity. The greenhouse gas contributions from this sector related to heating are significant. The technology is at the ready. Ownership is concentrated, and since we only turn over buildings on the order of 1% to 2% per year, we can't rely just on making changes to the easier to implement new building stock. But judging by the number of registrants, over 300, and the diverse range of fields you represent, I think that you all get it. Before giving you a brief overview of our program, I would first like to acknowledge our sponsors. And this includes the US Green Building Council, who does so much excellent work in this area, as well as BU's Energy and Sustainability Club, who is helping create our near-term generation of leaders. Let me give you a sense of the program. After our keynote speaker, we will have 3 short talks, followed by a longer Q&A session. You can enter your questions at the Q&A button, and time permitting, we will get to them. Our panelists will address commercial building decarbonization in 3 main areas. Kurt Roth will address small and mid-sized buildings. Gayatri Sundarajan will look at large buildings, and Mike Walters will talk about decarbonization at scale in terms of district energy systems. So it's now my privilege to introduce our keynote speaker, Dave Nemtsow, who has been the director of DOE's Building Technology Office over the last 5 years. David has a rich experience in energy, having been president of the Alliance to Save Energy, the Director General of the New South Wales Energy and Utilities Department in Australia, policy officer at an energy storage startup, and author of numerous studies on smart grid and energy efficiency. Most recently, he has been a leader in developing DOE's national roadmap on grid interactive efficient buildings. David.
Thanks so much, Professor Gevelber, and thank you to the Institute for inviting the U.S. Department of Energy to speak today on this central, essential, and thorny issue. How do we decarbonize our nation's commercial buildings? And before I talk about that, and if anybody expects to get answers and solutions on that in the next 15 minutes or even maybe the next 90 minutes, I think that's going to be a challenge, because this is one of the most complex energy and environmental issues that we face. And I'll tell you why I say all that and what we're doing, the U.S. Department of Energy, to lead that. I do want to also acknowledge, as Professor Gevelber did, that it is that COP26 is going on right now, and the timing for your session here at ISE is propitious. And I also want to acknowledge my close colleague, your Director Emeritus, Professor Peter Fox-Penner, who, as we speak, is in Glasgow, and he's doing something that's important. And if there are undergraduates or graduates or anybody in the field, Peter's doing something that's the most important thing we can do in our field. That is, he's speaking truth to power, and he's doing it right now in Glasgow. And that's essential for our work. And I think everybody on this panel knows that we are a lot of challenges, from status quoism to people who have a vested interest in the old way of doing business, and being able to speak truth to power will be essential. So thank you. Also, thanks USGBC, and I'm going to have a few special words to the BU club, because we're hiring at DOE. So I will admit I have a self-interest there. So look, let me go through a few issues, and again, I may raise as many questions as I answer. But there you go. And welcome the conversation. I thank you in advance for your work. I'm going to share some slides. Okay, so I'll just say I'm at the Department of Energy. I run something called the Building Technologies Office. We're part of a larger office called the Office of Energy Efficiency and Renewable Energy, which is part of the Department of Energy, which is part of the US government, which is part of civil society. And I'm not being flipped there. I'm serious. This is how we think about our roles and responsibilities here in our office. Look at that. Sorry, I had somebody else. I have a new animator for my slides, so forgive me for any mistakes. Here, I just wanted to look. I'm not a member of the administration. I'm a civil servant, and but I do want to talk about the Biden administration's very important, aggressive goals that are guiding the department, and I think are essential if we have any chance, if our species, Homo sapiens, has any chance of successfully tackling this issue. We need everything that the Biden administration has proposed. So I suspect you know all this, different goals that have been set out in different contexts to cut greenhouse gas emissions by half by 2030, to have a decarbonized power grid by 2035, and have a decarbonized zero net energy economy by 2050. I've been in the field a long time, as you heard. I get paid to work on buildings. So I think about all three of these. And buildings, as you'll hear from me in a minute, are both a recipient of the power grid, but also a contributor to the success of the power grid. And then obviously by 2050, we're not going to have a net zero economy unless our nation's 130 million buildings are at the heart of the solution. I'll say this about buildings. Buildings are the biggest energy sector in the country. And buildings consume 39% of US energy right now. 74%, 3/4 of US electricity is consumed in buildings, and even more at times of peak demand. Buildings contribute 35% or so of US CO2 emissions. In that case, we're second to transportation, and the others, buildings are the biggest. And more importantly, to a lot of other Americans, buildings spend over $400 billion per annum to heat and cool and light. That's just the utility bills. That's just the gas and electric, not counting fuel, oil, et cetera. Over 400 billion. And look, pick your number. At least a third of that is wasted, producing needless pollution. So the stakes are enormous. And buildings, again, 130 million of them. I know we're talking commercial buildings today, but it's all fair game. There's 5.9 million commercial buildings in this country, 123 million residential buildings, and then some in between, some mixed use, et cetera. Residential in total are a little bigger, about 21% of US consumption, than commercial in total are 18. And of course, within commercial, as we'll hear from our illustrious panel today, commercial buildings alone have enormous diversity. Size is the obvious one, and that's how we're organized today. But again, look at that picture I put up on the top left. Commercial buildings aren't just office towers, even though that's a lot of the action. You all are associated with university. They're educational facilities. They're healthcare, hospitality, warehousing, restaurants, retail, and all of those have different needs, different challenges, and different solutions. I'm going to talk broad brush today. Let me put in a pitch for my office and just tell you how we think in my office, so you'll know at least a few of my prejudices here. We're a comprehensive office. If you can see my hands, if you think of that spectrum of how we transform markets towards clean energy, towards a decarbonized future, that takes an entire spectrum of activities. I'm going to go from what's my right, I don't know what it is for you, called research and development. We support some applied, not basic research, but applied R&D in my office, working with the Department of Energy's national labs, as well as other players like BU and some of those lesser academic institutions in the Boston area, as well as around the country. And it turns out we just all learned that Michael and I were undergraduates together in Providence, Rhode Island. So I'll let you do the math on that, but you know, that's not a lesser institution, Michael, but those other ones are. But look, we support applied research in my office on a whole host of technologies. You can see everything we can get our hands on in the built environment: lighting, HVAC, water heating, windows, envelope, sensors, controls, slash smartness, slash grid interactivity. I'll talk about that in a minute, and building energy modeling, and more. Then we work to integrate them into the marketplace, because science experiments are fun, but they're not going to solve our problems. We need to integrate them. Kurt, I hope you'll talk about that. Fraunhofer is obviously a global leader in that issue of how we integrate new technologies so that people actually want to use them because they perform better, or they're cost effective, or they have lower carbon emissions, or all of the above. They're comfortable, more resilient. We have to validate, we have to give consumer tools so they can make informed decisions. And then we lock them in through mandatory regulatory mechanisms, such as building codes and appliance standards. I'm going to talk about both of those in a minute. But as you can see from the arrows, we're not done yet. Then it's shampoo, rinse, repeat time. Once we've locked in those savings, argon-filled, low-E double-paned windows, time to go back to the lab and work on triple-pane windows that are even more efficient, or new lighting technologies. So we have to keep going so that we can continue to make progress. And there you go. There's my animation to say it's a non-ending challenge to keep transforming markets through a host of things. Look, we can have a big debate, and I suspect you do at the Institute, about the role of R&D, the role of integration, the role of regulations. I'm an all of the above guy. I think it's like, what's more important, heart or lungs or brain kind of stuff. So there, again, my prejudice. This is a schema. This, oh, you can't see the legend. Sorry about that. This is actually, this is our projections looking forward. Oh, sorry. So the light blue is residential emissions due to electricity consumption. Then the orange is residential due to direct fuel use, oil, natural gas. Then the gray is commercial due to electricity, and then commercial direct use. And so let's stay on the second half of the slide in terms of decarbonizing. The point I want to make, and I'll make it different ways, is, and we're just doing commercial today, is we have these electricity uses and we have these direct fuel uses. And what we need to do several things to be able to decarbonize the commercial building sector. So, Michael, I assume at the Institute you teach the 7 Pillars of Wisdom by T.E. Lawrence of Arabia, because I'm mooching. I was inspired by him for some reason. So these are our pillars. I don't have 7, I only have 4 pillars of wisdom for decarbonization. And the 4th one's in parens. To decarbonize the commercial sector, I will say we need to do 3/4 things. So on the operational side, those are the 3. We need to use energy more efficiently. I hope in this audience, I don't have to explain myself. This is clearly a case where less is better than more, where we're going to get the same or better services from less input. That's what we've been doing for many years and decades. That's essential. Our job is still as much in front of us as it is behind us, but we have to expand the way we think. And those of us of a certain age, I already revealed that Gevelber and I are the same age, and Fox Penner is too, but those of us of a certain period have worked our careers on traditional energy efficiency. This is evolving now. Let me talk about demand flexibility, and I'll come back to that. This is a host of techniques and technologies so that we can shift when energy is used, not just use less of it, but shift when. So we can shift it off times of peak demand, when power generation is the most expensive, least reliable, and typically the dirtiest. We have to shift it to times when, as the nation uses more and more solar and wind power that are difficult to schedule, if not impossible, shift it towards times when solar and wind are plentiful, and away from times when we're more reliant on fossil energies. This is demand flexibility. It's a variant on storage. Just as storage shifts energy use over time, demand flexibility does the same by switching demand through advanced controls and advanced regulation. Third is electrification. And in this audience, I hope that's a given. Why electrification? Well, turns out electricity can be made by all sorts of things, some of which are emit carbon, some of which don't. Right now, our grid in the US is 63% carbon-based, natural gas and coal and oil, and 37% carbon-free. This administration has set a national goal, as well as many other jurisdictions have, to decarbonize the power grid by 2035, we hope. So electrification, shifting end uses from burning natural gas to clean electricity works if you do not one, but two things. One is that grid, those electrons need to be cleaned. That grid has to be cleaned up. And if so, then the end use, we have to shift technologies so that we can use electricity-based technologies, not just gas-based. So that means heat pumps instead of furnaces, or heat pumps instead of gas-fired hot water heaters. So it really, I should have said, beneficial electrification. The other part is there are clean gaseous fuels, such as renewable natural gas, such as green hydrogen. They're not in the marketplace yet. They're not at the 37% mark or close to it. That's why the focus on electrification, because electricity is further ahead. Then embodied carbons, in parentheses, this has nothing to do with the operations of a building. The first three include existing or new buildings. There's a lot of carbon embedded in the construction of buildings, in the materials, and in the construction techniques. This is a new emerging issue. It's not a new issue, it's an emerging issue, and that I think demands the attention of all of us. So that's what I want to talk about today. This is a fancy way, it's too many words. I don't know if you can see it, but if you look at it afterwards, you have to read this table vertically, not horizontally, just looking at these different pillars and how important they are. So this is just a key if you want to read it later. Energy efficiency is huge when it comes to decarbonization potential. I give it three stars. In other words, read it down. Energy efficiency can make a major contribution to decarbonization. Then if you go further, is energy efficiency major for reliability support? I would say no, it's relevant, but it's not major. That's how to read this. That's our way. Demand flexibility is huge for renewables integration, especially the variable renewables. But if you take anything from my talk today, it is we need to do all of the above. There's a line in our field that clean energy has no silver bullet, but it does, however, have silver buckshot. So I'm giving you a silver buckshot approach. We've got to do it all. And we've got to do deployment, we've got to do R&D. I'm going to let you read that at your leisure. I'm going to talk about these two whole building things, and then I will cease and desist, make one more pitch. I want to talk about grid interactive efficient buildings, and I want to talk about advanced building construction. And these are two keys to decarbonizing commercial buildings and residential too, but I'm going to talk about that. I'm going to start with advanced building construction. That thing on the left, the picture's sort of funny. That crane is not carrying a giant television set, which is what it looks like. It is carrying a modular constructed room. It's building a hotel as we speak. Why does it matter that room is built off-site on a modular basis? Because it's more energy efficient that way. We're still building buildings, whether it's residential or commercial, on-site with sticks or beams of steel, like it's a century ago. And if we can shift the construction to off-site, where we can use advanced technologies, we can have controlled environments, the quality in general is better, and the energy performance will often be better. And then we assemble them on site. And that's true for commercial, for res, as well as advanced materials. We can use 3D printing, modular construction. The technology revolution that's changing manufacturing isn't yet changing construction. In my office, we're working to do that. I also want to say at the bottom there, none of this is going to work unless our workforce, I suspect all of us on this meeting today love technologies. I suspect we all love the deployment of technologies. If we don't get the human beings who know how to do it, 1 out of 3 air conditioners in this country is installed wrong. Not manufactured wrong. It just something goes wrong with the installation. It's not properly charged. The Freon, the refrigerant's not properly charged. It's not the concrete pad it's on. It's not leveled. The ductworks don't connect. So unless we also have an advanced workforce, we won't have advanced energy. That's what our advanced building construction initiative is about. We're also using robotics to look at the thorny issue of retrofits. When we think about all those commercial buildings, how do we get into those weird spaces, especially if they have asbestos, and since we're worried about the safety of the workers, we hope robotics can complement the human workforce. What are grid interactive buildings? There you are. The occupant comes first. Well, look, if you remember the days when you went to an office or a classroom, you know that of course, there are lighting controls that turn the lights on or off if there's occupancy, but now we can use advanced controls in open spaces, whether it's an airport lounge or a cubicle-based space, so that we know the population, not who's there, but how big the population is, and we can run the air conditioning at an appropriate level. And if there's one person in the room, sure, the light needs to be on, but the air conditioning can run on low. If there's 150 people in the room, we need to crank it up. Even better is if we can use a signal from the utility company saying, hey, the system's stressed. Can you ease up for an hour? Some players, a hotel that's at half capacity, can ease up on its HVAC and make some money off the deal. Somebody else who's full out says, no, I'm not cutting back. That's what this grid interactivity is. If you look on top, that little icon for an algo, that's a smart controller, the microprocessor communications and algorithm and big data revolutions need to be harnessed, not just to make buildings smart. Smart is fun. I love my smart speakers, but smart is fun, smart is good, but we need to harness it for clean energy. Again, this is just telling you how we work. I'm just going to say one thing. I know today you want to talk technology, but just a setup for your next panel. Just remember this. You're going to hear from these. Just don't treat everybody the same. You know, if you say, oh, people care more about the cost of energy than its cleanliness, or people like solar, I just don't find that helpful. There's 320 million people in this country. There are so many different decision makers. You have to disaggregate. Trust me, Coca-Cola doesn't sell Coke by saying, oh, people like Coke Zero. They say college-educated Latina women in Chicago care about this and that and the other thing. And whether we get to that level or not, you see my point. These decisions, this is the silver buckshot, and we have a big audience, and they're hard to reach, and we have to think about the different ways we persuade them to decarbonize. I want to talk about the regulatory mechanisms real quick, and then I'll stop. First, I don't have a slide for appliance standards. My office regulates 60 different products, everything from refrigerators to lighting to ventilation, that use in total 90% of the operational energy in commercial buildings. We are taking a very aggressive approach with this administration to crank down the regulations. The technology is there. We need to insist that it's used. But let me talk about building codes. My office, the federal government does not regulate the energy performance of US buildings, with a couple of exceptions, manufactured housing and federal buildings. Most buildings are regulated at the state and city level, and we provide technical assistance, analysis, and encouragement to do it. If you look at the blue line here, the blue line is the ASHRAE 90.1 standard, looking at it over the last 40x years. And you can see, if you look at that index on the left, it's just a 0 to 100 index. You can see, if you can see my cursor, we've cut energy use by half in new commercial buildings. So anybody want to clap their hands? Anybody want to declare a victory? I am not among them. This slide is a Rorschach test. We got half done, and same on the residential side. You can see it's a similar trajectory. That's this pale green line. Oops, excuse me. But here's the half left to go. And look, this is not a goal of DOE net zero by 2030. That's not a formal goal. I'd love to get there. So we got a little over half done in 45 years, and in the next less than a decade, I want to get the rest of it done. That's a Rorschach test. That is achievable. This is a question here of politics and economics, not of technology. But there are a lot of different commercial buildings, and a high-rise hospital in Las Vegas is very different than a low-rise retail in Needham. Building performance standards. I'm playing to my audience. Look, this slide is old. Boston, it says under consideration. Apologies, you guys, not you guys, your home city here, or your city for a few years, has adopted building performance standards. Congratulations. And I also understand your mayor-elect, Ms. Wu, is a big supporter of that, so that's very exciting. Building performance standards are a key policy tool for dealing with existing buildings. Codes are primarily, not exclusively, primarily for new buildings to make them more efficient, and flexible, and electrified and decarbonized. Building performance standards say to existing buildings, crank it down. By year X, you have to measure how much you're using. By year Y, you have to publish how much you're using. By year Z, you have to improve it by X%. And then by year beta, you have to increase it by two times that, right? So it's a steady reduction path for existing building. This was pioneered by Washington, D.C. and New York City, and it's spreading across the country. And we're going to see what happens. And again, congratulations. Boston did two important things. I commend Boston, did two things that are not typical, more aggressive, and I think the way to go in the future. One is other jurisdictions, that shape I'm showing said reduce energy use. Boston said reduce greenhouse gas emissions, carbon dioxide equivalent. So that's CO2 as well as other gases. That's, I think, it's a more comprehensive approach. And two, Boston's more aggressive. The numbers, I can't do by memory the numbers that every jurisdiction who's adopted it so far has adopted, but Boston's going to get to zero faster, has committed to getting zero faster than others. So each jurisdiction, city or state, is going to have to do what works for them. But again, this is way for the future. Thank you. Here are some URLs. I know you're busy students. I know you know how to Google, but I'm just reminding you that my final pitch is we pay our fellows. Look, I was a free intern. Maybe you were too, Michael, back when. Man, we pay people now. I think it's a scandal, but the reality is you students are potential beneficiaries of that. We pay our fellows a lot of money, and we're looking for people. We're looking for engineers. We're looking for economists. We're looking for social scientists. We're looking for physicists. So we don't have, oh, don't go to that page. That page is for EERE. If you go there, you might end up with a gig in the solar office. Email me so you can end up in the building office. So I don't want to put my email address here and have some bot find me, but you can write to any of us at Efficiency Renewables, first.last@e.doe.gov. We have an opening right now as we speak. I'm instructed to tell you that our commercial team is looking for a fellow right now. I'm not making this up. It's typically 1 to 3 years. Did I mention it pays well? You can't be in school. You got to be done. It's a full-time gig. We're going to work you like a galley slave, and it's going to be the best gig you've had in a while. Thank you so much for having DOE today, and thanks, Michael and the Institute, for your great work.
Thank you very much, David. One quick question: having cheated and read your national roadmap, Grid Interactive Buildings, great technology. I'm glad you're supporting it. But as you described how you guys are going through multiple cycles to get this into industry, when I think about that, a lot of these exciting programs push into what the building operators got to do. And so the question is, what's your vision on how incentives, so currently the grid operators get paid for what they do, and now we're sort of pushing it into the buildings, and the buildings owners, one might argue, have to adopt some of those costs. So to actually get these technologies into the market, what do you see also needs to be done to provide them an incentive so that it actually happens?
Yeah, so I'm going to give you another one of these, all of the above buckshot kind of responses, right? So look, I think we have to do a lot of things, and let's take heat pumps, because heat pumps are such an exciting technology. They've been around for a while. You got a refrigerator, you got a heat pump, right? So they're proven, but they're not used a lot for water heating, and they're not used a lot for space heating. They are for space cooling, of course. So how do we push those? One, we collectively, and this includes utilities, includes government offices, have to demonstrate, validate, publish, demonstrate that they work, and they work in different settings. We're doing a lot of work on cold climate heat pumps. Heat pumps have always worked great. I live in Maryland, but now they work. We've advanced the technology, so we have to demonstrate that they work great in New England. because they do. There's one that's working right now in Alaska that's performing to 30 below. So but people have to know that. So we have to demonstrate and educate. Two, one of the big pieces of legislation before Congress, that famous reconciliation bill that goes back and forth, the $1.7 trillion one, includes major tax incentives for these technologies. So that's another way to incent people. A third way are the price signals. But a fourth way that I don't think gets enough attention is, and I think especially important to operators, is the role that utilities play. And for utilities that are regulated, such as National Grid and the ones in your neck of the woods, the public utility commissions need to provide incentives. We have decades of incentives for solar and efficiency. I think we need incentives for grid interactivity, more incentives for grid interactivity technologies, whether it's a smart thermostat or a heat pump for a restaurant, everything in between, so that there's a signal. Prices are a charged issue. In most commercial players, I forgot who's talking today, is it Kurt, about small buildings. Most small commercial utility customers in this country don't see time of use rates. They just see a flat rate. And so they need other kinds of incentives, such as rebates. So again, all the market pull called education, the market push, the market pull called incentives. And someday I think there will be a market push called regulatory mechanisms, but it's premature.
And one question from the audience, and I think you touched on it, but it came up again. What do you guys see in terms of hydrogen is coming in? So is it a time frame issue? How will it be done? And how important is that?
Yeah, can I give you one fact and one opinion? Would that be kosher? The fact is, hydrogen is coming in, and it's demonstrable. We see it in California, and with heavy duty trucking. The other fact is there's different kinds of hydrogen. There's blue, there's green. These aren't just for fun. These are important issues of decarbonization, because how you get, it's like electricity, right? Hydrogen is a carrier. So where the hydrogen came from affects whether it's a decarbonization strategy or just a something else strategy. There will be green hydrogen. The opinion part, and I've authorized some analysis, and if anybody has analysis they can share. I am nervous about the ability of green hydrogen in buildings, not because it's not used right now. You can take, I'm pointing to my water heater. You can take a cooktop or a water heater. You can mix up to 10% hydrogen into the pipe gas, and the burners will be happy. If you want to get above that, you got to make some tweaks. But what I'm concerned about is that buildings won't see our share of green hydrogen because other applications will pay more for it. Big industry and maritime uses, I think they're going to beat us to the punch. That's an opinion. I don't have analysis behind it, but I'm nervous about that buildings won't get our share of, and renewable natural gas has been a promise for a while, but the rubber hasn't hit the road yet on that. So that's why the emphasis on electrification. We know, right? We got a better track record on decarbonizing the electric power grid.
Yep, cool. Well, I'd like to thank David very much for taking time out of his busy day. And hopefully we can get his friend Peter to give us the update from what's going on in Glasgow, man on the street there. But I think questions are still coming in. David's probably got to shove off onto other things. And as some people have asked, the recording will be available, the slides will be available, and he just put out this job offer for anybody interested in making that transition. So I'd like to move along now and invite Kurt to present. He's our first panelist, and he's going to talk about decarbonization of opportunities for small and mid-sized buildings. And by way of big background, Kurt's been a leader in building energy systems for several decades now. He's currently the head of the energy systems at Fraunhofer Institute here at Boston University. Prior to Fraunhofer, he was a principal at ADL/TIAX, He has a PhD in mechanical engineering, studying aerosols, but you can't blame him for the aerosols from COVID. And he's an avid musician. So, Kurt.
Thank you, Michael. And appreciate the introduction. And I'll follow up on a specific topic that David touched on, some of the challenges around decarbonizing space heating in smaller and medium-sized buildings. Heartened about the increased focus on cold climate research, cold climate heat pumps, but there's some real challenges. I want to get into that. Really quickly, I work at Founder for USA. We're a nonprofit applied R&D organization that develops new technologies and also does field testing and evaluation to understand how they can be made more effective. Do a lot of work with Department of Energy, Building Technology Office. And one thing Michael encouraged me to do is to really kind of hit the summary of what I'm going to talk about first and then get into more detail. And really what I'm going to talk about is what you see right here. These things called packaged rooftop units, these modular self-contained units, which you see just populating the roofs of big box retail stores and vast majority of small, medium-sized buildings. These are low-cost options, but they're not maintained typically very effectively in a lot of cases. They lose because they have all these problems. They're not maintained. They have these faults that reduce their capacity, reduce their energy efficiency, and there just aren't cold climate heat pump products that can be dropped in to replace them. They don't really exist at any kind of scale in the marketplace today. This is feasible, but there's some other challenges that will make decarbonizing this part in particular of the commercial building sector very challenging. And that's what I'm going to get into today is kind of what's the landscape, why you should care about this, and then some of the challenges as well as some of the opportunities. And again, I think BTO is working on these opportunities, but it's a challenging market to crack. So we're talking about small to medium-sized buildings. What am I talking about? I'm talking about things roughly up to about 100,000 square feet. And this is vast majority of buildings. Out of more than 5.5 million buildings, you can see the distribution here. This is all but 150,000 of those. So this is a lot of buildings. And these buildings typically often do not have a central HVAC system. Many of them do not have a building automation system. And in a lot of cases, they don't have on-site building staff or someone to operate the buildings, the HVAC systems. This becomes more and more prevalent, these trends, as you go to smaller and smaller sizes. And maintenance, in some cases, it's done pretty effectively. In a lot of cases, people are just trying to keep up. Staff has been reduced. And finally, another thing that comes up is a large portion of these buildings are rented. That has some challenges, that poses some challenges in terms of how do you actually get technologies deployed in these buildings, because the people who pay the energy bills are not the people who own the buildings. So if we look at this by a floor space, these small, medium-sized buildings, they're roughly 2/3 of the commercial building floor space. Roughly a third underneath 25,000 square feet, and then another third between 25 and 100K. So again, there's a lot of floor space here, so a lot of energy in these buildings in the commercial building sector. A lot of attention paid to larger buildings where people have more sophisticated staffs. They have these central HVAC systems they can do more elaborate control sequences. There's a lot more fixed costs that can be, a lot of things can be leveraged across a larger energy footprint in those larger buildings, which just isn't available for these smaller buildings. And how are these heated and cooled? Again, for larger buildings, there's a lot of discussion of chiller plants, central boiler plants, but the real workhorse of this sector are packaged rooftop units. Again, these highly engineered products where you have heating systems, cooling systems, and ventilation systems all packaged together in one box. And this box, you can see it's mounted on the roof here on this thing called a curb. So essentially, you have ducts that go into the building, return back from the building. Here, you have outdoor air comes in through these kind of units here. Here's, for example, an outdoor air damper. And everything's contained in this box. Real estate is really precious here. And if you start changing the size of this box, Then you have to change the size of the curb, and then you have to do a new integration with the building, which increases its costs. But overwhelmingly, if you look at estimates for energy consumption for the commercial building sector in terms of HVAC, 60% roughly is in these packaged rooftop units. So, as I mentioned at the outset, there are a lot of packaged rooftop units. People have done field studies that find that they have faults. Faults such as duct leakage, where the heating or cooling does not go exactly where you want it to go. Refrigerant charge faults, where it's either high or low. If it's low, then you get cases where the effectiveness in terms of the amount of capacity and the amount of the efficiency of the unit drops, in some cases pretty precipitously. And then different kinds of fouling, where essentially your heat exchangers on the evaporator and condenser don't function as effectively as before. And then finally, economizer failure. This is something where a lot of buildings bring in cooler air when it's 55 degrees outside. They still need some cooling. They'll bring in the cooler air to cool the space. But if this outdoor air damper is open at a larger setting than needed just to provide ventilation air, and it's doing that when it's hot and humid outside or when it's quite cold outside, you have suddenly increased your building loads, in some cases dramatically. And that can have a significant impact, particularly if you have a very efficient building and the loads have gone way down, the shell loads, and now you've brought in a bunch more air that has to be conditioned. So these challenges exist for a large portion of these workhouse type of units and really compromise the real world effectiveness. Now, what's the challenge with space heating if you go to heat pumps? There's a lot of discussion going to heat pumps in the sector, and there are packaged rooftop units using electric resistance heating, particularly further south, and in some cases using heat pumps as well. Well, you can see if you look at the outdoor temperatures, it gets colder and colder. The heat pump capacity decreases, but at the same time, the heating load is increasing. And once you start going below this point where they meet, you have to make up this difference somehow. You have to have a supplemental heating system. A lot of times that can be electric resistance heating. And so this is a real challenge, and it really also brings out how important it is to reduce space heating loads through energy efficiency, things around enclosures, retrofits to reduce the shell loads, better windows, and then doing things with ventilation areas. Professor Gelber's worked on a lot. Those things have a real impact. So, but one thing that comes up frequently in this discussion is, this is something Michael and I have just talked about when he's rating Fraunhofer offices for coffee, is he's just like, install a hybrid heating system where you have a heat pump, which meets most of the load, and then you have supplemental heating from another kind of usually fossil fired system. But with a packaged rooftop unit, it's not so easy. You have these constrained boxes. It's tough to add additional units. You almost have to have another unit heating system in parallel. And that's a real challenge to do. So there are a lot of things that can be done. And this, again, gets back to a lot of things that David was touching on, maybe elaborate upon them, to get control of good performance at cold climate conditions. You can do a lot of things with controls, demand control, ventilation, reduce the amount of outdoor air you take into the building effectively. You can also do things like onboard fault detection and diagnostics. There's some products out there which help with that, although there could be much more of that done and more faults addressed by those kind of those products. And then there are things that coordinate essentially packaged rooftop unit operations among units for the same building owner to provide coordination and manage the peak load, provide demand response services. So things are available to help do this. And if you look at the cold climate kind of features, besides getting down loads and managing peaks and more effectively managing providing grid services, people can do things around variable capacity compressors. People can do parallel stages of compression, multiple stages of compression. They can do things around variable air volume and heat recovery ventilation. These can dramatically improve the efficiency of these products and also improve their capacities at lower outdoor temperatures to get there. But again, if you're doing all this inside this unit, you have to be really careful. This box size, it's reasonably fixed, and you can't change it too much, or you're going to be getting into some major work as part of retrofit in terms of changing what's going on the roof of the building. So there have been DOE funded projects to look at this for high performance units. This is work done by United Technologies Research Center, owned Carrier back then. And that was specifically, this was done 5-6 years ago. You can see at 17 degrees out, you're seeing the capacity, a 44% drop off in the high efficiency baseline. No drop off in capacity in this unit. Minus 13 degrees Fahrenheit, pretty darn cold, colder than it really ever gets around here in Boston. Normal unit, 71% capacity drop off, a COP about 1.25, but the prototype unit was almost a 2 COP and only a 15% capacity. So this is feasible, but there's a lack of market demand for these products. Gas heating is very affordable at this point in time. Why would someone switch? And also this technology is not proven in the marketplace. The products just aren't there at this point in time. So another approach that people were talking about, and this is something that you can see the Northwest Energy Efficiency Alliance, they're talking about, is an approach which works pretty well in new buildings where you can do something where you have a dedicated outdoor air system, which brings in the outdoor air, and then you meet the space conditioning loads, besides conditioning that air, the other loads through a combination of ductless mini split heat pumps, variable refrigerant volume systems, potentially ground source is another kind of approach, which is very interesting and can work in some cases. But if you're thinking about this for a retrofit, what's the rub? Cost. They're very expensive to put in, especially when you already have a packaged rooftop unit in there in the first place. Now you're adding a whole second system, and you're adding premium systems in there. And you look at these cost data from different sources. Now, these are very, very rough approximate costs, but you can see it's it's, you know, these existing options, packaged rooftop units, are much more affordable than these other ones. So it makes it very challenging to do it from a cost effectiveness point of view. Things need to change. This is where technology development to integrate these in, get the products out there in packaged rooftop unit formats could really help in terms of market adoption. And final thing I just want to touch on, last slide, is really looking at what's going on with rented spaces. This is a particularly vexing portion of this. So a lot of cases, the lease is structured where the energy costs are passed through to the tenants. And so you have the classic split incentive situation where the people who pay the bill are not the ones who buy the equipment. And also you get to smaller buildings. If you want to put something in there, the cost of negotiating a transaction relative to is not, will scale somewhat with size, but there's some fixed cost to it, and that's going to be more important for smaller buildings. This is a challenge with energy efficiency programs in general. And also, if you need to raise capital, well, that's often a problem. Smaller businesses often have that issue. And they would also really want to do it to invest in their core business where they know what they can do. They know, they really know that very well, where they have, you know, can really get a much better return in a lot of cases, potentially. And for them, energy costs currently are not that big a priority, regrettably, but it's, you know, it's a small, relatively small portion of the operating costs, and they just don't have capacity to do that. And in some cases, finally, I guess I would add that there's a lot of first cost sensitivity. Making longer term investments, they, you know, some cases the time horizons for businesses, for people investing in these mechanical systems, they're pretty short time horizons. So the high first cost is challenging. So in sum, I think there are a lot of challenges, particularly in this sector. It has a big impact in terms of decarbonization of commercial buildings. There are approaches that can hopefully get us there, but there's a long way to go in terms of getting those really proven, demonstrated in the marketplace to really be in a position where they can drive adoption.
Well, thank you very much, Kurt. I think you really do a great job of pointing out how important this sector is, and this particular portion of the sector, and how challenging bringing solutions to this sector is going to be. And it's got to be driven. I don't think it's a technology issue, as you've been talking about, but if we're really going to make a dent in that area, it's really got to be more regulation, policy, economic sort of issue. So I think we'll move on to our next speaker and get some more questions from you at the end. Our next speaker is Gayatri Sundarajan. And here she's showing up. And Gayatri is a senior in mechanical engineering at BU, and she's going to be speaking about her study of how BU can decarbonize its major buildings. Gayatri's extracurriculars have included being a member of BU's Student Rocket Propulsion Group, an amazing group of students who, build things, test them out, and keep moving rocketry forward. A number of them have gone on to great companies out there. And currently she's an intern at Commonwealth Fusion Systems. So Gayatri, take it away.
Thank you so much. So hi, everyone. Today I'll be talking about the technical and economic considerations to make when retrofitting large commercial buildings, and discuss a strategy that we've analyzed in our research team to achieve a deep and quick decarbonization by combining different heat pump and boiler systems. One second. Throughout our work, we've been motivated by the following research question, and that is, how can we electrify the greatest percent of BU's fossil heating systems in the shortest time, meeting building heating requirements and capital and operating budget constraints? As a note, we've conducted our research at Boston University, but the strategies and takeaways that we've developed or come across are applicable to Boston and beyond. How we've tackled this question is by looking at different technical, financial, and environmental aspects of a retrofit. Specifically, questions we've asked are, what are the existing building heating requirements? How important is reducing the capital cost of a given retrofit in order to enable faster retrofits of a given building portfolio? And what are the greenhouse gas emission reductions expectations for each of the strategies that we've discussed? In order to achieve this sort of decarbonization, the first thing I'm going to touch on is different heating electrification technologies, and these are ones that have been discussed earlier in the seminar as well. Generally, the two categories of electrification systems we've been looking at are heat pumps and boilers. In between them, you'll notice that heat pumps have a much greater efficiency, but are also much more expensive than boilers are. Within heat pumps, you'll see different categories, air source versus ground source, and this distinction is made based on where they have their thermal reservoir. Air source heat pumps are less efficient than ground source heat pumps, but are also about 2 times less capital intensive. The other trade-off you can look at is between high temperature and low temperature heat pumps. And high temperature heat pumps have heating fluids that are more compatible with existing perimeter heat exchangers, so between the 170 and 180 degree Fahrenheit range, but are also less efficient and require more capital than a low temperature heat pump. And as we've mentioned earlier, these heat pumps are less proven in the market. And so you're going to find smaller sizes or systems that are more in the validation phase. So what you can notice here is that there's certain trade-offs that we can take advantage of. The fact that the heat pump systems have a higher efficiency, but also a higher cost, and that boiler systems are less expensive, but also less efficient. So that's something we'll be looking at in the presentation moving forward. So in order to determine what system to develop, first let's look at the technical requirements of retrofitting an existing building. The key considerations we've made are the following 4. We've looked at the impact of a required heating power on equipment sizing. We've looked at the capacity factor of equipment and how that impacts utilization, and then we'll be looking at the greenhouse gas emission reduction that we can expect from each of these strategies. We've looked at the heating fluid temperatures that we can expect or that we require for existing building heating exchangers and what we need throughout the heating season. We can also look at the impact of increased electrical demand on the electrical supply that we have on the building and whether we might need to expand that to accommodate an electrified heating system. All of these key considerations come into the following question, which is which configurations and combinations of heating equipment can best meet the technical requirements for retrofitting an existing building. What we'll be talking about first is the first constraint, so the required heating capacity. As we've mentioned earlier, as temperatures decrease, we need more heating capacity. However, the number of hours that we actually spend in each of these temperature bins doesn't vary in the same way. What we've noticed is that for temperatures that are greater than 30 degrees Fahrenheit, we spend roughly 700 to 800 hours in each of these 5-degree temperature bins. However, there's a sharp drop-off for temperatures colder than 30 degrees Fahrenheit, to the point where you can spend between 10 and 15 hours in an average year at these coldest temperatures. So what we asked ourselves is there a way that we could design a system that includes heat pumps and boilers to take advantage of the fact of when most of the heating energy will be used, and size our more expensive and more efficient equipment for that point, and use boilers for those coldest days. And so what we determined was that we can have our 30-degree temperature be our switching point. So we find that if we install heat pumps for temperatures that are greater than 30 degrees Fahrenheit, we would install 45% of our peak heating capacity with heat pumps, and this would service 80% of the heating season duration. And what we would do for the remainder of the heating season is that we would use conventional electric boilers. And these systems, as we mentioned, are less efficient, but are also less expensive. And so what we're able to do here is we're able to reduce the capital cost of our total retrofit while maintaining the thermal comfort throughout the year. Another question that you might ask with a hybrid system is, what is the utilization of our heat pump as part of the system? And another question is, what is the expected greenhouse gas emission reduction given that the whole system is not run by heat pumps? So in order to understand utilization, we have a value called the capacity factor, which is able to quantify the percent of time you use an expensive piece of capital equipment. What we find is that for a hybrid system where you install the heat pump for temperatures greater than 30 degrees Fahrenheit, that you can actually double the utilization of your expensive heat pump. You can see here we've gone from 31% to about 64%. At the same time, you notice that we no longer have 100% electrification. But what we do have is we are able to achieve 90% decarbonization. And how we're able to achieve this is that we're actually using, we're taking advantage of the fact that most of the hours are spent at temperatures that are greater than 30 degrees Fahrenheit, and each of these temperature bins doesn't require as much heating power as we do in the colder regions. So what we're able to find is that we can size a system where we have heat pumps for temperatures greater than 30 degrees Fahrenheit, and we're able to increase the utilization of that heat pump, as well as maintain 90% of our carbon emissions from our existing system. Something else to consider is heating fluid temperatures. As we mentioned earlier, our systems are our existing heat exchangers run at between 170 and 190 degrees Fahrenheit. But our question was, could we use a lower heating fluid temperature in order to make ourselves be able to use lower temperature heat pumps, which, as we mentioned, are lower capital and also higher efficiency. So what we found is that we can actually use 130-degree hot water when the outdoor air temperatures are roughly greater than 31 degrees Fahrenheit. And so what this means is that for that heat pump component of that hybrid system, we can actually use a low temperature heat pump instead of a high temperature heat pump. And what we can do is we can use a natural gas boiler or an electric boiler for supplemental heat on the coldest days. And this will actually provide us with higher temperature heating fluid in addition to decreasing that peak electrical demand at that point. And so now we're looking at a hybrid system, which is sized for a heat pump for temperatures greater than 30 degrees Fahrenheit. We're using a low temperature heat pump there and looking at the natural gas boiler for supplemental heat on the coldest days. And then as a note, this is still able to achieve that 90% decarbonization that we mentioned. The last constraint to consider is the impact of electrification on increased building electrical capacity. Our question here was, will new electrical capacity have to be added in order to accommodate peaks in our hourly electrical demand during the coldest days of the heating season? The way that we were able to analyze this is by looking at our current cooling season peak demand, which is 1.6 megawatts, and looking at our current heating season demand, which is 1.1 megawatts. And what we found is that if our heating electrification solution will, even if our heating electrification solution will increase our existing heating electrical demand, as long as it does not exceed the cooling season peak, we can actually keep our existing electrical capacity. And so what we've done here is we've modeled implementing this hybrid low temperature air source heat pump and natural gas boiler system with our existing electrical capacity. And so what we found is that since we don't exceed this cooling season peak, we don't need to engage in an expensive and cumbersome electrical capacity upgrade in order to achieve that 90% decarbonization. It is important to note that when I mentioned we don't need to engage in a electrical capacity upgrade, that doesn't mean we don't have any electrical work to do. And we will likely have to expand the electrical panels within the building in order to allow for the distribution of the electricity to the heat pumps. So just as a summary of the elements that lead to this hybrid system, we found that when we look at the technical requirements of retrofitting an existing building, we can actually achieve these technical requirements in a way that is cost efficient when we use a hybrid system. We noticed that they're compatible with the heating fluid temperatures that are required for existing buildings. We've also noticed that we can increase the utilization of heat pumps by 2 times. We can reduce the equipment capital cost by roughly 50%, and we can achieve this 90% decarbonization without upgrading our building's electrical supply. And it's also, I just want to note that this strategy is applicable for both air source heat pumps and ground source heat pumps. And just very quickly, I just want to jump into a financial outlay of these different options. What you'll see in the middle is the 2 hybrid solutions that we've discussed: low temperature heat pumps and natural gas boiler hybrids. And what we have here is in the orange column, there's capital costs. In the red dots, you have the annual operating cost, and then the green columns are net present value of total expenses. What you'll notice is that the hybrid systems represent a net cost increase from our business as usual case. You can call this our natural gas boiler, the fossil baseline. But what they do represent is a cost cut from what a completely heat pump system would look like. When you compare these 2 heat pump systems, one is air source and the other is ground source, you notice they have a very similar net present value of total expenses. However, the ground source heat pump system requires about 60% more capital in order to implement. And this is where our capital limitations come in. The idea is, given a limited capital budget, if we can design these electrification solutions to be as little capital intensive as possible, then we can achieve the retrofits of more buildings than we would otherwise, and able to decarbonize their portfolio quicker than we would with more expensive retrofits. And so, as I just keep this summary slide for fast and decarbonization on screen, I just like to leave you with one thought, and that is that decarbonization is accessible for building owners of large commercial buildings, and that there are strategies beyond looking at total heat pump or total boiler systems that we can explore to transition into decarbonization. And that we can keep in mind the technical and financial, as well as environmental considerations and constraints when we're determining what's the best system for us to employ in a given building. And with that, I'm just going to pass it back to Professor Developer.
Cool. Thank you, Gayatri. I think in looking at the clock and making sure we get enough time to have Mike Walters' important contribution, we're going to move directly on. I will notice that someone put in the comments, they've done exactly what you're talking about, and it worked great. But it is climate, depends on how cold you're getting. So let's move on to Mike Walters' talk about how do we develop systems at large scale where you're got a whole heating system for a large area that you want to try to retrofit. Mike is a principal at Salis O'Brien, and he's got over 20 years experience in building energy systems. He has a BS in architectural engineering and electric power, and he works out of the Madison, Wisconsin office and is doing exciting, I think Salis O'Brien is doing great work across the country. So without further ado, Mike.
Thanks very much. I think I got off easy there. Kurt had a few decades of experience, and I only had 20 years. So that was good. I saw him put up his 2 fingers. There's only, you wanted to be a little younger too, but thanks for the introduction. And I think what I have to share fits in real well with what was just shared for the commercial building side. In fact, I thought we could have probably intermixed every other slide of my talk into hers because it fits very well. Just a brief introduction to Salis O'Brien. We're a large national engineering firm that does anything from energy planning all the way to design, implementation, and commissioning of buildings large and small. What I have up here on the screen is more related to the talk today, and that's specifically sort of decarbonization planning and implementation projects at scale throughout the country. You can see everything from work we've done for Stanford University and the far West Coast to things that we're doing in the Boston area, and it's quite active actually throughout New England. Right now, I'm going to share some project examples of mostly completed work. Some is currently in the planning or design stages, and just to give you a flavor of what can be done at the campus or district scale and how impactful that effort can really be. The first project I wanted to talk about is Ball State University. This is a project that has been done for a period of years now and is kind of well published in the market at this point, but it's a large district system that is 100% a ground source heat pump conversion project. So unlike the hybrid systems that were just discussed, this is 100% a conversion from coal-fired boilers feeding a district steam system to a large ground source heat pump system. Here's some conversion facts, right? This is a pretty big system. It's 7.1 million square feet across 47 buildings. It is a really central strategy to their overall decarbonization for campus, and they're about halfway through their goal to completely decarbonize the campus within the next decade. I won't go into the details of this system in a lot of specifics, but if there are questions, please let us know and we'll happily respond to those. What I did want to talk about relative to this project was this idea of the hot water supply temperature and its impact on not only the equipment that you select for creating that hot water, but also the conversion cost of the building themselves, right? These existing buildings have existing heating and cooling components that need to change when you make a major shift of the campus supply systems. And what we often do for district settings is do setback tests in the period of the year that we're about to enter here, right? So the November through sort of early February timeframe will offer you a very cold window of opportunity where you can start to set back the supply hot water temperature in the buildings. And instead of do expensive modeling or expensive testing or metering of various spaces, you really rely on human beings to be your metering device and issue cold calls to your facilities or to the program manager for this kind of effort. And you can see here at Ball State, we started at 180 degrees and we moved all the way down to 130 degree hot water temperature and found which buildings were really going to create issues from a comfort perspective. And that allowed us to pick the hot water supply temperature that would be most cost effective to do the building conversion work. And we let that drive the technology selection and the ground source heat pump plan and the distribution system and the distribution piping to really figure out how to balance cost versus effectiveness. And we'll talk about other campuses and the efficiency gains or potential gains that are left on the table if you make different selections. But Ball State was designed for 150 degree hot water. It actually operates these days at about 140 degrees as a hot water supply temperature. The next project I want to briefly touch on is a difference. It's not a college or university campus. This is an industrial research setting. This is a Ford Motor Company's campus in Dearborn, Michigan, which is a research and development center for them in North America. You can see this project this is the new central plant that we designed and master planned as part of the project, and it is for a major redevelopment. This image is the master plan concept for the demolition of 4 million square feet on this campus and the addition of 6 million square feet to put the overall campus at about 9 million square feet of occupied space, which is a collection of research settings, engine test cells, as well as a lot of office and pretty typical commercial space from an officing perspective. The central energy plant is in the lower right corner of this. You can see there's a very large thermal storage tank, as well as the smaller tank is a fire protection tank. And the concept for the central energy plant there is far more like a hybrid system here. This is a mix of very high temperature industrial or research needs. So there's steam use that will be maintained on this campus, but also a lot of low temperature hot water use as well. So here we're transitioning from 180-degree steam heated buildings to 120-degree hot water supply temperature for space conditioning, and doing that through a collection of right-sized heat recovery chillers, a ground source heat pump system, and then steam to hot water conversion off of cogeneration assets that are servicing a large electric load for this campus, as well as the need for steam in a collection of buildings here. There's also the 5 million gallons of thermal energy storage that is a chilled water storage tank in this setting. Again, that gives us more runtime on certain assets and ability to dispatch in a much more flexible way a collection of very complicated assets in that central energy plant. Switching back to the university sector, Miami University in Ohio has been on about a 10-year transition plan there to convert, similar to Ball State, to almost a wholly geothermal ground source heat pump system. And it has been doing that much more on a district level. This is an energy station that is complete now. It's got heat pumps installed in it and is their newest ground source heat pump plant. But they're looking to convert a pretty large campus, again, a 7 million or so square feet there in phases, in districts, as it makes sense with their capital improvement program as they renew the facilities throughout the campus to update for program needs or just for deferred maintenance on the physical plant itself. This is a really interesting project in that we have very good measured information around how this transition has improved the energy efficiency of the campus, the carbon intensity, and really the cost savings that have been derived from this strategy. So again, it's a steam system being transitioned to a low temperature hot water system. You can see here a 56% carbon reduction, a very similar change in their energy use intensity, and generating about $9 million of annual utility cost savings and $200,000 of chemical treatment savings on an annualized basis there. This program has been so successful that Doug Hammerly, who is the campus director of this, has transitioned actually to working at South O'Brien these days to help other campuses throughout the country sort of adopt this methodology, and he's super enthusiastic about its potential broadly in higher ed as folks look to meet the American College and University President's Climate Commitment using strategies like this. I wanted to just briefly touch on the temperature versus cost versus efficiency sort of strategy here. And it's very important to select the hot water supply temperature, not only for the technology selection on the heat pump side, but also perhaps more importantly on just the cost of the building conversion. So I put in here, sort of 4 different projects that we've been associated with recently. Ball State, I said, was designed at 150. It's operating in the 140 range now. Miami is a 130 project. That Ford project I mentioned is all the way down to the 120 degree end of the spectrum. And that really is, it's a really important balance to really carefully consider how much money will be required to be deployed to change terminal units, to change air handling pieces, to change lots of mechanical components throughout the building stock if you're going to really press the issue on how low you can put that hot water temperature. But of course, the lower it goes, the better you can use an air source heat pump, and the more efficient any heat pump strategy will be to meet that demand. And then a couple of other project examples. This is both new construction and a link to a major piece of low-income housing. This is in New York City. This is in Long Island City specifically, and a major development that is being considered on Long Island City. That you see the high-rise portion of that is approximately 12 million square feet of development, and the low-rise buildings that are kind of in the distance are approximately 3 million square feet of low-income housing. And here again, this is a very hybrid-like multi-technology solution set on the supply side, but the overall strategy is electrification and certainly leveraging heat pump technology very aggressively. So you got ground source heat pump energy, you've got a strong footprint trying to get at river source cooling and heating actually, so a water source heat pump there again, and then looking at wastewater energy recovery as well. So the waste stream associated with sewage systems or wastewater systems can really be a very large component to a hybrid model for looking at heat pump energy sources. And then switching gears very drastically here, this is outside of Toronto. This is single family or very low rise residential development. I put this in here only to suggest that there are lots of ground source heat pump models and ground source heat pump with air source heat pumps integrated with them that are being looked at, and there are test cases and real developments happening throughout North America in cold climates that look at using these technologies as efficiently as possible. And I know National Grid and Orange and Rockland are two utilities on the East Coast that are doing pilot programs for this as well. And this is a single pipe ambient system through about a 300 home development outside of Toronto that uses ground source heat pumps and vertical heat exchangers integrated in the public right of way. And last topic here I really want to touch on is air source heat pumps. I think our previous speakers certainly spoke to how cost constraining the ground source heat pump strategies can be, and that's very true. They can be difficult from an affordability perspective. Air source heat pumps do offer really good alternatives, even at scale. You have to look at beyond the typical technologies here. Here I'm showing an ammonia air source heat pump, which has its operational issues, certainly, and you need to be careful about operating ammonia systems, but it can operate down to 0 degrees Fahrenheit and produce water up to 160 degrees Fahrenheit. So if you're looking for higher temperature solution that can minimize your building conversion costs, this kind of technology can be utilized, and certainly Johnson Controls, Daikin, Multi-Stack are all looking at producing systems like this, just to name a few manufacturers. I think an important thing to consider, though, as you look at air source heat pumps is their coefficient of performance needs to be relatively high if you're going to compare them from a cost effectiveness on a dollar per kBtu basis with a gas boiler. So, this is an illustration based on the work we did at University of Miami in Ohio and using their utility rates and that system specifically. But it is really important, like the previous analysis showed, to look at the outside air temperature, at what kind of production temperature you're trying to make on the hot water side, and really what that balance point is on the outside air temperature and where you want to select and operate your equipment long term. And then finally, my last slide here is we think about the space challenges associated with ground source heat pumps all the time, the amount of land area that you need or how to do that underneath the building and all the other constraints associated with that. But large air source heat pumps are not small pieces of mechanical equipment either. This just gives you a sense of trying to provide enough capacity for a 500-ton system. That's a pretty big footprint that you're looking at there. That's 60 feet versus 60 by 500 or by 50 feet rather. To get this Evapco unit, you got to find roof space for systems that are that large. If you're doing large commercial or district systems, these are not easy systems to site and locate either. So just making that a point as well. So with that, I think that's my last slide, and maybe we salvaged a couple of minutes for questions yet here.
Thank you very much, Mike. And what I love about your presentation, it's reality. These are projects you've actually worked on, currently working on. One question I have for you is, over the last, since you didn't like my, you wanted 2 decades sort of thing, over the last decade, how have you seen people changing what they're actually doing versus and the motivation for it? So the theme here was decarbonization to help us meet our climate objectives. So, and you talked about, also cost. So are people doing this transition because their systems are broken down and old, they need to replace them anyways? Are they thinking about decarbonization, and has the pace of these sort of projects increased over time?
Well, first off, I'd say the pace of the projects is maybe overwhelming the engineering community right now. So there's certainly a lot of future in being an engineering professor and being an engineering student, because there's a lot of need for this kind of thinking in the world. I think you know, the first time I started to do this kind of work in the college campus setting was doing climate action plan for Cornell in 2007, 2008. And back then, you know, they were one of few institutions that were really thinking seriously about this and about the challenging side of it, right? There was energy conservation activities that were kind of beginning to be built in a serious way, but energy conservation is super important and it should be the first order out of the gate, but eventually you get somewhere down the line with energy conservation where you have to pull the trigger on a big, gnarly infrastructure investment that's difficult from a human capital, a financial capital, and from a phasing perspective to pull off. And I think higher ed across the board, specifically from a campus kind of district setting, that everybody's thinking very seriously about how to make that transition. What's the appropriate time frame? What's the appropriate phasing schedule for that? And how they mix it into the capital renewal that these large systems, you know, are going to need to have to implement. And that is cascading, right? As Ball States out there, as other sorts of major district systems have been developed, private developers are following suit, large industrial companies are coming on board with those kinds of planning activities too. I mean, 5 years ago, we did not see, you know, the industrial sector or the you know, the automotive sector, you know, coming into play with their facilities on these kinds of topics. And across the board, those kinds of users and district systems are being assessed and implemented too.
And I liked how you presented your work on shockingly lowering the temperature of the working fluids. How do you help the facilities managers not freak out that you're going to break their system? And I think you were explaining you do it sort of experimentally. Can you say a little bit?
We do, yes, definitely. I mean, we certainly, you know, map out a plan with them, which buildings are likely to be successful in that kind of just slow setbacks scenario, which ones are likely to get, you know, cold calls for, what the human interaction aspect of that is going to be when you get it, what kind of communication strategy happens in advance of implementing a program like that. So everybody knows, look, something's going to fail. We're expecting that to happen. Please call us when it does and we'll quickly fix it. But it's very cost effective. It gives great insight to people. And it's shocking how much existing capacity to heat buildings has been pre-engineered into buildings or conservatively engineered into buildings in the last 40 years. And there is significant capacity out there, even on, you know, campuses that are 100 years old or more. We find that lots of buildings have the ability to heat with lower temperature hot water. At Ball State, for instance, you know, a strategy we used there was instead of ripping out large air handling systems and doing major modifications, we did minor retrofits so that we could use the cooling coil in an air handling unit as the heating coil and have essentially two heating coils in the air handler for periods of the year. We're also looking at CO2 heat pumps to integrate into systems that do domestic hot water and other sorts of strategies. They're relatively small, like 25 tons, but they have very high lift. They're very interesting systems that are coming out for that too.
Cool, thanks. Kurt, somebody brought up a question on, we've been talking about decarbonization, but how do we also ensure that we maintain good air quality within these buildings? We spend 90% of our day in buildings. So any comments you want to provide for that?
Sure. I mean, I guess what I can mention is that this is where in these buildings addressing the faults is important, making sure that the ventilation systems are actually providing the amount of outdoor ventilation air that is required for different spaces, because there are a lot of packaged rooftop units suffer from faults, damper faults. They might not be balanced properly. In fact, I imagine in a lot of cases they're not balanced effectively. So I think those are key factors in terms of making sure you bring in the amount of ventilation air. And the other thing is controlling sources in the buildings themselves, right? So you want to bring in the outdoor air, but you need to manage the indoor sources and essentially use materials and that don't create problems. Part of that also comes down to making sure you don't create different issues with the enclosure. For example, you don't want to have situations that might create mold conditions favorable for mold growth, which is a real problem.
Cool, thanks. Gayatri, a question brought up for you was, you got us down 90%. How are you going to squeeze out that last 10% of carbon?
Yeah, this is a really great question and something that we, just didn't have time to go into. What we had talked about in that hybrid strategy is that we were going to be using a heat pump for about 90% of that decarbonization, and then we were having the remaining 10% from the natural gas boiler. What we had looked at as a completely decarbonized solution was exchanging out that natural gas boiler for an electric alternative. As I've mentioned in that comment, in there, some things to consider when doing this is the impact on electrical capacity. This is probably the point where you have to consider increasing electrical capacity, which is much more expensive than doing any work inside the building. Something else to consider at that point as well. Let me just make sure I have the right comment there. Another piece to consider is what to do in the case of an electrical outage. With the natural gas system, you always have a backup in that case. You might need to consider something like storage or another form of energy that you would use to provide heating, especially in a lab building or in a dorm building, because you don't want all your heating to go on that coldest day. And the likelihood, if you have this on a campus, is that that coldest day is the same day for every single building. So it's really the worst case scenario. So I think keeping that in mind when going to 100% decarbonization is important, and also considering that the 90% decarbonization is a great point to kind of validate the process, get yourself and your campus ready for 100% decarbonization and really take that leap.
Cool, thank you very much. And I think we are out of time. Lots of great questions coming in. And a month from now, we're going to continue the discussion. The discussion is going to focus more on the policy issues and the financial issues. So we have another great panel of people together, including how do you raise money for this sort of conversion, as well as what it's going to cost. So thank you, panelists. Appreciate the audience with your great questions. These, as I mentioned, this will be, the video recording will be posted, and I think we'll try to get these presentations posted as well. Thank you very much. This has really been an exciting and informative day. And as I think we all know, we really have to be moving on these issues to try to maintain 1.5C. And I think we pointed out solutions, but also some of the problems that we need to really focus on. So thanks again, everybody, for being here.